So now I have fixed the specimen back at the center, and then here we have a valve, black color valve, to increase or decrease the flow of water in the cooling section. So this way you close the valve, and this way you can open the valve to have like maximum flow. All right, so there is a lot of cooling here, so there is big delta T and a lot of heat. You can allow a lot of heat to move from the left to the right side. Then I want to turn this so you can see the cooling system. This is the water pipe inlet, okay, and here it goes to the right side, and then this is the exit. After cooling the bronze material, it comes out here and it goes back into the drain. So this is the drain facility. So inlet and the drain pipe going towards the right side, trying to keep this one cool. Okay, so this is all about the hardware, and now we are going to go to the schematic diagram. Same thing represented here. 3 sections, left, right, and the central section, and you have the location of the thermocouple sensors to measure the temperature T1, T2, T3, T4, left side, and then middle you have 5, 6, 7, and from 8 to 11 on the right side, plus you have SC2, which is the flow sensor for the water which is going on the cooling side. It is a sensor. T12 will measure the temperature of water before it goes in there, and T13 after it comes out from the cooling section. So you can also measure that and know the delta T, how much of heat is given to the water there. And VR1 is the valve, black color, to increase or decrease the flow. Okay, so now let's go to the computer hardware, or I must say the computer interface. Right here on the screen we have T1, T2, T3, T4, all of those sensors displaying the data here up to T11, 12, 13, then SC2, and you have SW1, which is the heat input, still not yet on. Okay, so in this panel here, right side, you could see all of the data, which is the real-time data when the machine is in operation. So let us say our specimen is at the center. So if I need to look at the specimen temperature right now, T5, T6, T7, I'm going to look here. T5 is 27.7, and I have T7 is 28.5. all right, although I need to check these numbers, but sometimes the thermocouples are interplaced, but once we supply the heat, then we can make sure how is the movement of heat, because T5 must be greater than T7 because the heat is coming this side. So T5 will receive the heat first and then it goes to 7. So we can check the numbers while we run the machine in some time now. Okay, so here we have 6.9 liter per minute is the water flow rate that is going on the cooling side, and right, so a lot of measurements are made here, but like I said, in our equation or for this particular exercise in the data sheet here, we have T5 and T7 to be collected, and then with that we are going to calculate the K value. So I will go one page up here. There is an equation for K, Q by A, delta X by delta T, which is for the length of the specimen. So Q is the heat input, 5, 15, 20, 25, 30, that we change. A is pi d square by 4. Like I said, the inner material there, stainless steel, inside the insulation, the diameter you use to calculate the cross-section area. Delta X is the length of the or the thickness of the specimen, and delta T5 minus T7 we get it from the data here. Okay, so let's start the heat input. So I'm going, right now SW1 is 0 watt, and there is an actuator here with which you could increase or decrease the heat given to the left side. Now it is 12.9. okay, so if you make it 100 here, you see the maximum possible heat that can be supplied to the system is like around 115 watt at this point in time. Okay, so I don't want that much heat because the manual says start with 5 watt first, so I'm going to adjust this and bring it close to 5. Okay, right, so I consider 5.3 as 5 because sometimes it is difficult, there is a lot of fluctuation, so I consider this as 5 watt, the first heat input condition, and I give the system at least 5 to 10 minutes of time to become stable, and then once it became stable I am going to record these temperature T5 and T7. Okay, so that is the first set of data in the table here. We have set heat input 5 and we are going to record T5 and T7, that is delta T for our specimen, and then the last column is calculation. Next reading I need to give heat input 15. So again I come back here for with the actuator control I am going to increase so that I reach 15, close to 15, and then I am going to wait again at least 5 to 10 minutes. The system becomes stable, there is like good movement of heat from the heating side to the cooling side through our specimen. Then I will record again T5 and T7. Okay, then I am going to go to the table which says next is 20 heat input. So again with the help of actuator control I am going to increase this to 20, right? Okay, so I consider this as 20. Again wait for 10 minutes, the system becomes stable, the heat moves from left to right, and I measure T5 and T7. Then I go to 25. Okay, so this I consider 24.2, right, 25. So there is big fluctuation here, so you can consider this one as 25, and then same procedure, you wait till the system becomes stable, record the temperature. The last case is 30 degrees, so I'm in 30 watts, so I'm going to increase it further, and I consider this as like 30 watt. Okay, so this is the last step. Again I will measure T5 and T7 after waiting for 10 minutes because I want the system to become very stable, so by that time it becomes stable. As of now you can see T5 is 33.3, T7 is 31. So here this is high temperature T5, T7 is low, which means there is movement of heat from left to right and through the length. So based on the material, copper, aluminium, steel, or let's say brass, there is the movement of heat either quickly or slowly. Okay, so that is what is we are referring as thermal conductivity, is the ability to transfer the heat at a given rate. For example, some materials transfer very fast, some materials transfer very slow. Okay, now you can save the data using this option. You click save data here. Every 1 second it is going to save, and somewhere it will give you an Excel file. It will make an Excel file with the saved data. Okay, right. Or as such you could take from the screen, you could just read from the screen T5, T6, T7, once you set the condition, you could read from here. Okay, so there are either ways. You take it from Excel file or you directly read from this display here. Okay, so I think that is all about this experiment. Where we have tested stainless steel. Some other case, some other day, you can bring a new material like copper. You can put inside here copper and repeat the experiment same way, and then we can find K value using the equation. So we are trying to find the K value with the help of a mathematical equation by making use of some temperature measurements for the given specimen. Okay, right, so that I click stop here, and then all of the data is frozen there. So that is all about this experiment.